Hi, kids. It's Mr. Cosby. I'm here to talk to you about radioactive decay and how it could be used to measure the age of old things. This lesson requires you to remember our periodic table of elements and what elements are in general. Here's that periodic table of elements again. And yeah, for instance, number one on our periodic table, hydrogen. What made it hydrogen is it has one proton inside the nucleus of that hydrogen atom, which is different from helium, which has two protons in it. Anyways, to our actual lesson here. Here you're looking at, well, my horrible drawing of air. And by the way, I didn't draw this quite right. Nitrogen atoms, which are what you're seeing here, they're actually usually stuck together in pairs, N2, not N1. But I'm just simplifying for this drawing. What I'm pointing out here, or why I'm pointing this out, is because the air you're breathing is not oxygen. We learned this earlier this year that most of the air that you actually breathe is actually nitrogen, 78% of it. Only a small fraction, about 21%, is that oxygen that your cells need in order to do cellular respiration. That oxygen is very important. It's just not making up the majority of the air that you're breathing. Well, what does this have to do with reactive decay? It's the fact that nitrogen makes up the majority of the atmosphere, and that's the entire atmosphere from where you're sitting in your house right now all the way up to nearly outer space is mostly nitrogen. Here is an atom of nitrogen. What makes it nitrogen, thinking back to the periodic table again, just the number of protons in its nucleus. In this atom of nitrogen, there are one, two, three, four, five, six, seven protons. And if we look at the periodic table of elements, right here, nitrogen, N, has seven protons. That's why that number is associated with nitrogen. Every atom of nitrogen in the universe has seven protons. If it had eight protons, it would be oxygen. If it had six, it would be carbon, right? So yeah, here's a nitrogen atom. Along with the protons, this nitrogen atom does have other types of atoms, other types of subatomic particles like neutrons. Neutrons here, there's one, two, three, four, five, six, seven. So there's seven neutrons, and one, two, three, four, five, six, seven electrons. Okay. Well, when it comes to talking about radioactive decay, the amount of protons and neutrons really matter, not so much the electrons. In fact, chemists add up the number of protons and neutrons to get a special number that they call the atomic mass. Atomic, yeah, sorry, kids, I'm writing with my mouse. This is not the easiest thing. Atomic mass. Well, it's supposed to be an S right there. The atomic mass is a measurement of mass, but down to the size and scale of atoms. And what you need to know is that protons and neutrons, they're pretty big. They're massive compared to electrons. Electrons are tiny. My analogy is if you and all of your friends got on to a bathroom scale, yes, it'd be a tight fit and you wouldn't be social distancing then, so that'd be bad. But you'd weigh some amount, maybe several thousand pounds. Then if you all got off of that bathroom scale and each of you put a grain of sand in your pockets and then got back on the bathroom scale, well, one grain of sand isn't going to change your mass very much to that bathroom scale. Same kind of idea is going on with atomic mass. Protons and neutrons are huge. Electrons are tiny. We tend to ignore electrons when talking about atomic mass. How chemists calculate atomic mass is they just add up the number of protons and neutrons. Well, we already did that for you. Seven protons, seven neutrons. The atomic mass of nitrogen is 14. Now, to sound fancy, like you're a chemist, most chemists wouldn't say just nitrogen. They'd actually put that mass at the end, call it nitrogen 14. It describes that nitrogen atom just a little bit better than just saying nitrogen. All right, so taking too long on this. Let's keep going. So here's how this is important. That nitrogen 14 that's floating around in our atmosphere, it's getting hit by sunshine all day long. And sometimes, every now and then, let's see, magic pen. Here's some sunlight coming out of this, out of our friendly sun here. And yes, the sunlight goes right through the particles of air all around us and reaches us here on Earth to allow things like photosynthesis to happen. Every now and then, something interesting happens where a photon of light leaving the sun smacks into a proton in the nucleus of a nitrogen atom in just the right way that the proton is actually it actually absorbs that sunlight. It takes it in. And what does that, she changes the proton into a neutron. That proton is no longer a proton, it just turned into a neutron. It's kind of cool. But this has a significant impact on this atom because now, if you're thinking correctly, this is no longer going to have 7 protons. It's got 1, 2, 3, 4, 5, 6. It only has 6 protons now. And likewise, no longer does it have 7 neutrons. It's got 1, 2, 3, 4, 5, 6, 7, 8. Now it has 8 neutrons. And you'll notice I didn't even put the electrons on this slide because who cares about them for this? So yeah, we just changed this. And let's go back to our periodic table of elements. Look, it's got 6 protons now. Is it still nitrogen? The answer is no. Now it's carbon. Carbon are the atoms have 6. This sounds a little bit like reactive decay, doesn't it? We just change one atom into another by changing a proton into a neutron. Now, instead of nitrogen, we have a carbon atom. And so yeah, this is no longer nitrogen, it's carbon. That's supposed to be an R there. Looks like a V. Fix. That's carbon. But we do need to consider that, look, the atomic mass of it, 8 plus 6, is 14. So if you look at the periodic table and find the atomic mass of carbon, it's normally 12. This atom is carbon 14. That sounds unusual, as if it's not normal, as if it shouldn't be that way, as if maybe this atom is unstable. That's right. I hope you're thinking what I'm thinking, which is that carbon 14 atom, it's radioactive. That's right. It's not normal. It's ready to undergo radioactive decay. Of course, it's pretty much just a typical atom, except now at some point that the energy that went into the proton to turn into a neutron, it's going to come back out again. And when it does, that atom that's carbon 14, it turns back into nitrogen 14. That is radioactive decay. Okay. Now, what you need to realize is, well, the sun is still shining down on our atmosphere. And so all day long, every day, a few atoms of nitrogen get smacked into by sunlight and turn into carbon 14. That happens all day long. And when is the sun not shining? Haha, I know you just said at nighttime, but think about that. At nighttime, isn't the sun still shining on Earth? Yes, just not on the side of the Earth that you're on. So this process of nitrogen turning into carbon 14, it happens all day long everywhere on Earth. And we're in a state of balance. Carbon 14 is constantly being generated at about the same rate that carbon 14 is decaying through reactive decay back into nitrogen. So we have this stable level carbon 14 in our atmosphere that's been that way for, well, ever and ever and ever, as far as we know. As long as there's been nitrogen there and as long as there's been sunlight, we've had some carbon 14 in our air. So now back to our drawing of our atmosphere. Look, here's the carbon 14 atom. This is unusual. Carbon in general doesn't really belong floating around in the air. Um, it's an unusual atom to have up here. And carbon happens to be a fairly reactive atom. That is, it wants to stick to other atoms and make molecules. And you'll notice there's some atoms around it that would love to stick to it and make a molecule. In particular, this atom of oxygen and this atom of oxygen. Now, we don't have a radioactive carbon 14 atom anymore. We have a radioactive carbon dioxide molecule now. And yes, even though that carbon is radioactive, it's just a normal atom as far as other atoms are concerned. They don't know that's radioactive or care. It's their atoms. They're just going to stick to what other atoms they can. So that leads us to this is radioactive carbon dioxide. And who likes carbon dioxide? Do you remember? That's right. Plants do. And this plant will take in that radioactive carbon dioxide and turn it into radioactive sugar. That's a process I think you learned about several months ago. Photosynthesis. Remember photosynthesis? Yeah, so now that radioactive carbon 14 is being used in the plant to make sugar. That sugar might end up in the cell wall of the plant cells as cellulose. This plant is now radioactive. Hey, by the way, oh, and I should mention, the plant doesn't recognize it has radioactive atom in it. It's just an atom as far as the plant. But to keep on going here, who likes plants? That's right. This cow likes plants. And so this cow is going to eat this plant and take in the radioactive sugar molecule, it's in the carbon, and transfer it into itself. Where now some of that radioactive carbon 14 is now in this cow. Yay, the cow's reactive. And realize it's not just this cow, it's any animal that eats the cow, because the cow ate the plant, but that was radioactive. Now the cow's reactive. Now, if I don't know, say a hawk comes down and eats the cow, now the hawk's going to be radioactive. So all these living things happen to be radioactive, right? Where's my drawing? Here we go. Oop. So here is our radioactive cow. And yes, you should realize all living things on Earth are radioactive. We all take in carbon 14 because plants take it in from the atmosphere, and we animals or other plants are always taking the stuff in. And so, yeah, we're all radioactive, and that includes you. You are slightly radioactive. Speaking of this cow, though, when does the cow get rid of its carbon 14? When does it get rid of its radioactivity? I said never here, but it does. All day long, it's losing carbon 14 through radioactive decay inside of its body. But every time it eats, it takes in more carbon 14 to replace it. So the radioactivity of our cow stays the same. Well, until our cow dies. Sorry, don't worry. The cow lived a long, healthy life. He was a very happy cow when he passed away. Now, here's how this is useful. Yes, I'm finally getting to the point. So, we have some level of carbon 14 there. I don't know what it is, some parts per million, I would say. And our cow, shown at the bottom of the picture here, while it's alive, it's constantly taking in carbon 14, and carbon 14 is decaying in it. So the cow, while it's alive, it has about the same level of carbon 14 as is in the air. And then look, this graph is time on the x-axis. So as time goes by, our cow friend died eventually. And what's going to happen to the carbon 14 levels? They're going to start to decrease in the cow because, well, it's no longer taking in new carbon 14 atoms. So let's try to show that in a graph. And yes, it's going to be real fun using my mouse to draw this. But yeah, while the cow's alive, the carbon 14 level in the cow remains roughly the same as is in the air its whole life. But then we reach some point in the cow's life when it dies. And when that happens, the carbon 14 in it is going to start to disappear. It's going to drop off. And it drops off following this thing called an exponential decay curve. where someday there'll only be 50% of the carbon 14 in the cow as there was when the cow was alive. And as the carbon 14 disappears over time, boy, my graph is really ugly. Can I draw this? Try this one more time. So yeah, it should look like, yeah, it looks a little better. It should look kind of like this. Then someday there'll only be 25% of the original carbon 14, and so on and so on. Well, hey, we have a saying for this. When there's only half of the carbon 14, it's right here on my graph now. When there's only half of the carbon 14 in it, we say that one half-life has gone by. So on my graph, this point right here-ish represents one half-life for carbon 14. And then when there's half of the half, 25% of the carbon 14, that's when another half-life, two half-lives. Lambda here, by the way, is the Greek symbol lambda. It's used to stand for half-life by people that do this a lot. Then at someday, there'll only be 12.5% of the carbon 14 left. That's where three half-lives are. So why is this so useful to us? Well, look, imagine you're a paleontologist out hiking through the desert when one day you come across a fossil or some old cow bones. You take a sample of this fossil, bring it back to the lab, and you crush it up in a special machine that actually can count the number of carbon 14 atoms present in the old fossil. And then you can compare that to what it should be. And if you know, for instance, that there's only, I don't know, 12% of the carbon 14 in your fossil, as is in the air, you know that three half-lives have gone by. And if you happen to know the half-life for carbon 14, which is equal to 5,200 and, oh no, I'm doing the wrong thing. What is it again? 5,740, I believe. 5,740 years, then hey, you now know, well, three half-lives have gone by. If you multiply this by 3, you can get the answer of how old this thing is. Let's see, 22 carry 2, 17,220 years old. Isn't that cool? Guys, we can use carbon 14 in fossils to determine not how long ago they were born, but how long ago they died. This represents how long after death. So this is how we use carbon 14 to figure out the age of fossils. Now, there's other techniques because carbon 14 is not in everything. We can also measure the age of rocks. Rocks don't do photosynthesis and they don't eat plants, so they don't have carbon 14 in them, but they do use, well, they don't use, rocks do contain some elements that we can use the same process in. For instance, this is on one of your slides. Uranium tends to be found, well, uranium is a reactive element, and we can use that same sort of decay curve to figure out how old the rock is. Most common way we do this is we look at zircons. Zircons are a crystal that forms in many igneous rocks. See at ZR, it's one of the elements on your periodic table. And if I can find it, I don't even know where it is on here. Oh, right there. ZR number 40. That's zirconium. Zirconium happens to be an element in, I guess zirconium is the element. So ZR in, zirconium, sorry, is in zircons. That's the element. And when igneous rocks are cooling off, sometimes that ZR gets replaced by uranium. It does not ever get replaced by lead, Pb, which is what uranium eventually turns into. So we can take a crystal of zircon, crush it up, and we can count how many uranium atoms are in it compared to how many lead atoms. Well, when this first cooled off, there's going to be zero lead in it. But as time goes by, the uranium that's in it will turn into lead. And so the more lead you get, the more time has to have gone by. We can use a reactive decay curve, just like we did for our dead cow and carbon 14, to figure out how many half lives have gone by for a crystal of igneous rock. Um, Anyways, hope this helps you to understand how we use reactive decay to measure the age of fossils and rocks a little bit. Thanks for listening.